I think we can start. Good morning, everybody. Welcome to the webinar of this year to celebrate the International Day for Combating Sand and Dust Storms. I'm Emanuele Emili from the Barcelona Supercomputing Center, and I'll introduce you to Sara Basart from the World Meteorological Organization, who will help me introducing the speakers. The webinar of this year will be focused on forecasting mineral dust with a special attention to how to use satellite observations. And there will be one of the talk going to be given in French. So you have an option in the Zoom. I hope that you can find it to show captions. And this could help if you don't understand French. You can activate that during that talk. I will then let the floor to Sara. Thank you, everybody.
Thanks a lot for the introduction. I think that most of you know me because you saw me in several events these last days. We are here to celebrate the International Day to combating sand and dust storms. And why this day? Because the General Assembly of United Nations proclaimed 12 July as the International Day for combating sand and dust storms. And this day is aiming to raise awareness about the importance of this hazard for health and sustainability. Also, I want to mention, maybe you know that, but in 2018, United Nations General Assembly also launched this United Nations Coalition for Combating Sand and Dust Storms that is now a group of more than 19 agencies from UN, but also non-UN agencies that are trying to coordinate efforts to promote mitigation and adaptation strategies to combat sand and dust storms. And this year, we are starting the United Nations Decade for Combating Sand and Dust Storms, and the topic is to create capacity building in the regions to really help the countries to overcome the impacts posed by this natural risk. And the slogan is rising from Africa to China, but we know that sand and dust storms is a global concern, not just because sand and dust storms are coming from big deserts, it's also the small sources that are appearing worldwide and is having impact in our life. In this context, you have to know, because you are now watching one of the webinars promoted by this WMO Barcelona DAS Regional Center. WMO launched in 2007 the International Research Program on Sand and Dust Storms, which is the Sand and Dust Storms Warming Advisory and Assessment System. This SDS that is an international effort that is organized also with activities in specific regions. And in the map, you can see the 4 active regions that we have at the moment linked to the SDS. Each region is also connected with a regional center that is coordinating the activity. And nowadays we have 4 regions and 4 centers: Barbados for Pan America, Barcelona for the North Africa, Middle East, and Europe, Jeddah in Saudi Arabia for the region of the Gulf Cooperation Council countries, and Beijing in China for the region of Asia. And as you can see in the image, the need to create regions is because each region is having a specific needs and requirements, and the strategies that we have to implement needs to be done at regional level. This is more or less what you know about the SDS as an international coordination effort of research connecting weather and climate communities. Also, we are working a lot in the identification and assessment of sand and dust storms impacts. We are promoting the use of current available products, and this means observations and forecasts, and the Barcelona DAS Regional Center is a good example of this kind of platforms that we are trying to promote. And also we are working a lot to create capacity building in the countries and the regions and to facilitate the access to these services and products. And one of the examples of the things that the community is doing in this kind of effort to promote science for services is we are publishing community papers, we are providing technical recommendations on atmospheric composition and specifically for sand and dust storms, but also we are contributing to international reports and articles. And here you have the summary of the latest publications that was promoted by the Sun and Dust Storm Warming Advisory and Assessment Community, which is the annual bulletin that we launched the last bulletin last week on 10th July, because we are trying to link the launch of this bulletin with the International Day, but also recently we were having these guidelines on Sun and Dust Storms mitigation strategy that is going to the promotion of impact-based forecast. Also the review that was led by one of the members of the North Africa, Middle East and Europe partners, Barbara, that is doing the review of the impacts on the aviation for the impacts of sun and dust storms in the aviation sector. And also more recently in Lancet Countdown, that is one of the international journals for climate and health studies, we achieved to manage to include a new indicator connected with sun and dust storms. And just to finalize, this is the latest bulletin, and as you can see, this is the annual snapshot of the year 2024. And as you can see, it seems that in sources we are having a decrease, but the transport is getting more and more emphasized than previous years. And you can see the full report, the full bulletin in the link that you can see down in the bottom of the slide. I want to invite you to take a look. There are some pieces coming from the North Africa, Middle East and Europe community. And all your contributions are always very welcome to this annual bulletin. Remember, every year we are publishing this bulletin. And with that, I will move to introduce the speakers of today. And the first speaker that we have today is Sophie Vandenbussche. She will have a presentation that is focusing in the products that are coming from MetOP IASI. Sophie is a well-known researcher in the satellite community. It is based in Belgium, in Brussels. And she was working for a long time on the validation of satellite data, mostly ozone, and developing new methods. And in 2011 is when she started to work with the thermal infrared aerosatellite retrievals. And she nowadays, probably, correct me if I'm wrong, Sophie, is your main activity in VIRA, in your institution. And also now, apart from that, she's adding greenhouse gas retrievals to this portfolio of products coming from IASI. And she's very active in many projects and communities like Aerocom, Aerosat, or ICAP, some of the well-known aerosol modeling and satellite communities at international level. And with that, Sophie, I will pass you the floor, and I will invite you to share your screen. And yeah.
Okay. Thank you, Sara. Just 1 second to make it right. This goes up here. I hope you see it nicely.
No.
That window is always okay. That should be okay now, right?
No.
No.
Now. Now is okay.
Okay. So thank you. I will start these webinars with, let's say, explaining unusual satellite data. People are mostly used to the aerosol observations in the visible. In my case, I'm working with thermal infrared observations. So first, just very quickly, it doesn't want to go out. Very quickly, to show you the wavelength range we are interested in. So it's ranging from, let's say, 8 to 12 microns for the dust signature. And the IASI instrument is measuring a broader range in that thermal infrared spectral range. So it's a spectral range where you don't have solar light, and it has different important physical properties to consider. So for the emission, the source of the light that we are observing, instead of being the sun, here we have the Earth's surface as the source, depending then on the temperature and the emissivity of the surface. And we also have the atmosphere being a source of radiation, depending on all that is in there and on their optical properties, so gases, aerosols, clouds, everything. And it depends on their temperature. The emission depends on the temperature. Of course, you have the atmosphere being a sink for the radiation, so absorbing and scattering the radiation that was emitted earlier. And this is then occurring due to the presence of gases, aerosols, and clouds, so everything in the atmosphere. You don't need any solar light, so you can observe day and night, which is pretty interesting. The signature of the aerosol is very specific in the thermal infrared. First, you have absorption and emission. For this, you need specific optical properties, and these will link the absorption and emission to only minerals. So that is why in the thermal infrared, you can only observe mineral dust and volcanic ash aerosols. You don't see the biomass burning aerosols, the black carbon, or these kind of things. Then you have scattering. Because of the large wavelengths, the scattering is only the coarse mode particles, so the big particles, because we are looking here at about 10 micron. So what you will see in the thermal infrared is mineral aerosols like dust, and only the large particles. The rest doesn't have a signature. And then there is an issue with the clouds that we have to filter out somehow, and it's always difficult and never really perfect, but we do our best. Now you have also something very interesting is that you get some sensitivity to the altitude due to the fact that the thermal emission from the aerosols will depend on their temperature, and the temperature depends on the altitude. So you get some sensitivity. The IASI instrument is satellite flying. It is a nadir instrument, so that means it's looking directly to the Earth's surface. And it is scanning across the path to have thousands of kilometers observations for one orbit. And with that, you get almost global coverage twice per day. The footprint is of 12-kilometer diameter if you are right below the satellite, and it grows larger at the extremities because of geometrical deformation. These satellites fly on sun-synchronous orbit, so that means that the local solar time is the same everywhere when it measures, plus minus 1 hour, let's say, and it's 9:30 morning and evening. Up to now, 3 satellites have been launched, the first one in 2006, so we have data since 2006. And the future satellite with a slightly improved instrument is planned to be launched later this year. So you can have long time series and start climate studies with it. Now, an example of some results you can obtain. So this is using our algorithm, our retrieval algorithm. On the right, you have the 10 micrometer dust AOD obtained with that algorithm for a day where there was a very intense dust storm, the Godzilla dust storm in June 2020. And on the left, you have to compare with the MODIS true color image. And you can really see that the plume shape and location, they match pretty well. And then you see on the right, in the AOD map, you see the white spots. It's either between orbits or when you have a cloud. And you can clearly see that the clouds are well removed if you compare with the MODIS plot. But when there is a thin cloud, it's sometimes a little bit more tricky. Now, this is just to quickly show you what it looks like, this signature of the dust in the spectra. So if you are not specialist in spectra, don't worry, it's just half a minute. This is an example of a IASI spectrum outside the dust plume over the ocean. And this is the example of a spectrum within the dust plume. And you can immediately see that strong difference around 1,000 centimeters minus 1, which is corresponding to 10 micron. And you see that V-shaped signature. This is really the signature of dust. Sometimes it's not that clear, but basically that's the signature of dust. Now, our algorithm is called MAPIR for Mineral Aerosol Profiling from Infrared Radiances. The main product is a vertical profile of dust concentrations, and we have 10 layers of 1 kilometer centered from the surface to 9.5 kilometer altitude. But even with 10 layers, we have 2 to 3 degrees of freedom. So that means 2 to 3 independent information. That means not all these 10 layers are independent. There is some correlation between them. And you will see in a plot later how you can really observe that. As byproduct, we also provide integrated dust AOD at 10 micron, which is the reference wavelength for the thermal infrared. And we also provide the converted AOD to 550 nanometer. And I will explain in a second what you have to be careful about when you use that converted AOD. We also calculate the dust mean altitude. And then more technically, for people needing it to assimilate data or whatever to analyze in depth, we have averaging kernels and an error analysis. So for the conversion, what I meant is if you convert the AOD from 10 micron to 550 nanometer, you need many assumptions on the particle optical properties. So that conversion clearly increases the uncertainty of the AOD. And of course, you convert only what you were able to observe at 10 micron. So you will have AOD at 550 related to the coarse dust particles and with the sensitivity of a thermal infrared instrument. So I will just come back to that sensitivity in a few seconds. This is an example of the profiles we can get for, let's say, a day in June 2018 when there were multiple dust events. So on the top, you have again the AOD from IASI. On the bottom, you have the vertical profile from the retrieval along the black line on the AOD map. So if you start on the west side, you see over the Atlantic, there is a transported plume with relatively high altitude between 2 and 4 kilometers and a little bit of deposition, it seems. Then in the Sahara, you have a really strong emission event with a lot of dust close to the surface and also higher up, up to 5 kilometers, even a little bit up to 6 kilometers. And then in the Middle East, you have two more localized dust events at low altitude, and that seem to be more confined. So you see here that we can have some impression of the dust altitude and vertical distribution, but it's not extremely precise. You never see only one layer and nothing in the layers around. It's not really the same as with a LiDAR. So the take-home messages. First, let's start with the difficult points. The sensitivity issue. So if you are over cold surfaces or low AOD, the signal is very small, and so it's difficult to get good data. Also, if the dust layer is at a similar temperature as the surface, then the emission and the absorption compensate, and you only get the signature of the scattering, which is pretty low. Then you have very low sensitivity. And also one thing to keep in mind is, I said it's mineral specific, but it's actually silicates that matter. And because of that, the locally emitted high latitude dust is not observed because it doesn't contain silicates. The good point now is that it is mineral specific, so you have really dust information. You don't have to separate and to make additional assumptions to separate. It's pure dust. You have nighttime observations in addition to the daytime, and you have some vertical sensitivity with almost global coverage twice per day. And then finally, the links to where you can find the data. And with the data, there is always a lot of documentation. We have data since the beginning of the IASI dataset in July 2007 and up to now. You can find the profiles on our institute website, which is the link highlighted in yellow. And you have everything also on that website, the links to the other places you can find the data. And finally, I wanted to mention that there is some work ongoing with the ACSAF from EUMETSAT to deliver near real-time data through their usual channels. So hopefully this will come before the end of the year. Fingers crossed. And with that, I want to thank you for your attention.
Thanks a lot, Sophie, for being on time. Really appreciate it. And we have time for one quick question. If you can raise your hand or maybe to use the Q&A or the chat for your questions. Also, we can save your question and take care at the end with the panelists. Then I cannot see, there is one hand. Franco, one very quick one.
Thank you very much, Sophie. Very interesting and concise. My question is about the conversion between the wavelengths. is, I understand you rely on assumptions, but do you have, let's say, I quickly ask, do you have a fixed conversion or is it varying over different locations? And is it like a factor or something like this? And has it been tested against MODIS or other sources of visible AOD?
Thank you for the question. It's an interesting one. It's a fixed factor that was calculated from the optical properties of the dust that we use in the retrieval, which is fixed. And the value is 1.78. So it's fixed everywhere along time and space. When we compare the data with IRONET, we see clearly some underestimation with IASI, with the converted IASI data with respect to IRONET. So I think we could revise this factor by using the validation information to get another value, which will probably be more close to 2.5, something like that. But to start with, we had to get some kind of physically based value, which is containing a lot of uncertainties.
Thank you.
Thanks a lot, Franco, for your question. And use the chat if you have more questions or you want that some of the experts will answer any question. But in the meantime, we will move to the next speaker, who is Melanie Ades. Melanie is a senior scientist at ECMWF, the European Centre for Medium Range and Weather Forecast. She's part of this Copernicus Atmosphere Monitoring Service, which is CAMS, and she's really specialized in the use of aerosol and dust optical depth satellite observations to improve the CAMS dust forecast. And also she's member of the steering group of the SDS of the region of North Africa, Middle East, and Europe, but also on top of that, she's also a member of the global committee that is coordinating all the activities of the different regions and initiatives. And it's my pleasure, Melanie, if you can share your screen to pass you the floor and give us this short talk about the use of satellite observations in this operational system that is providing global products, but also the regional European ensemble is using the CAMS Global as boundary and initial conditions for the regional forecast. Then the 10 minutes is yours.
Thanks, Sarah. Is that all okay? You can see the screen fine?
Everything good.
Great.
Yeah.
Yeah, as Sarah says, I work as part of the Copernicus Atmosphere Monitoring Service, or CAMS. And in this talk, I really want to look at how we use satellite observations to really improve the model results we get from the CAMS model in terms of the dust forecast that we produce. So the Copernicus Atmosphere Monitoring Service, or CAMS, is part of the Copernicus programme, which is the Earth observation component of the European Union space programme. And I always sort of see it as being divided into two parts, the Copernicus programme. You have the satellites, which sort of do the direct observation of the Earth. And then you have these 6 thematic information services, and they're there to really take the satellite observations, the retrievals, the raw data, and turn it into something that is more readily and easily usable by European citizens. So that could be small, medium-sized enterprises, that could be researchers, whoever needs to use this data, but perhaps using the raw satellite data or the retrieval data is not so easy for them to sort of look at trends with using that data. So we're really about converting the raw satellite data from these Sentinel satellites into information that can be more widely used. And the CAMS service, the Atmosphere Monitoring Service, we really look at atmospheric constituents. So this is things like greenhouse gases, trace gases, ozone, and of course, aerosols. So the CAMS service is again divided into 2 different parts. We have the global model, which is run at ECMWF, or the European Centre for Medium Range Weather Forecasts, which is where I work. We run a global model, so we really look at how trace gases and aerosols are sort of vectored and transported around the globe. And because it's a global model, we run at a slightly coarser resolution of 40 by 40 kilometres. And then tied to that, we have these 11 regional models that really just cover the European domain. And those are at a high resolution, they're 10 by 10 kilometers, and they use the data that comes from the global model as the boundary conditions. So all 11 of these regional models all use the same boundary conditions. The 11 regional models also all use the same European CAMS emissions, whereas the global model uses different global emissions. But both the regional models and the global model use the GFAS wildfire emission system to really sort of track and monitor how wildfires develop and change over time. For the global model, we use satellite observations to sort of inform and update our model and to keep it tied to what's going on in real life. So these are satellite observations of things like aerosol optical depth, ozone, carbon monoxide. The regional models, although they're starting to investigate, and some of the models might use satellite observations, they mainly use these sort of surface air quality observations. So these are ground-based stationary observations that can be used over the European domain to really sort of improve and tie the models to real life. So how do we use these observations in the CAMS global system? We have this sort of cycling system that goes on. So what we do is we produce a short 3-hour forecast. And we look at that. This is on a sort of grid, so it's on our 45 kilometre by 40 kilometre grid. It goes up through different levels of the atmosphere, so it really captures all the information that we want to have in a model and want to be able to share with our users. But it's just a model, and so we can use the satellite observations to really kind of constrain that model to sort of tie it to reality and make sure it's really capturing what we can observe from satellite observations as going on in real life. But of course, the satellite observations don't tell the full story anyway. As Sophie said, there's gaps because of clouds, there's the overpass times of the satellites, there's data with the swath that perhaps doesn't quite cover the full globe. And it's also for AOD, it's a total column, total aerosol observation. So it doesn't give us quite the same information as the model that's the information that users might be interested in. And so what we do is we look at the satellite observation, we look at the forecast, we have errors associated to both, and we kind of form an analysis that is our best guess of what the current situation is in the atmosphere, taking into account our model and where we need to have this information, but also taking into account the observational information that we know is really showing what the real situation is. And from this best guess, from this analysis, we produce both a medium range forecast. So I show here, this is a forecast for last week. There's been a whole sequence of Saharan dust storm events that have been affected across the Atlantic this year. And so this is one that was going on last week. And you can see this is our 5-day forecast, and we produce these twice a day. And this data is freely available, it's quality controlled, anyone can download the data and use this data. And then from this analysis, we also produce another short-term forecast that goes into our next cycle, where we again compare to the new observations we have from satellites and produce a new best guess of the atmosphere, which now takes into account these more up-to-date observations. So we just keep going on and on like this. So what aerosol observations do we use within the CAMS system? We primarily use 3 different instruments, MODIS, VIIRS and PMAP, on different satellites. So MODIS we use from the Aqua and Terra satellites, and then VIIRS from NOAA-20 and SMPP. PMAP is a combined instrument product, so it uses several of the different instruments on board METOP B and METOP C. VIIRS is probably our dominant observation, I would say, just because it's such a high resolution measurement that we really get a lot of information from it. But we really need all those different observations within our system because they provide different information, and satellite observations can vary even if they're looking at the same scene. They have different overpass times, and so we really want the combination of all those different satellite observations within our system. We're also monitoring a new observation from the Sentinel-3 satellite from SLSTR, again to give us some different information. All the satellite observations that we use are at this wavelength of 550 nanometers that Sophie's already mentioned, and they're aerosol optical depth, so they're all aerosols. And it's also a total atmospheric column. And as Sarah said, it's daytime only. So again, this is an observation from that dust storm last week. You can sort of see the hint of it in the observation off the coast of Africa. And you can see there's these large gaps. And this is because this is all the information that goes into the forecast we produce starting at midnight. And these are midnight UTC. And so these gaps are the situation where it's nighttime when these observations are made. And this goes into our aerosol model in the CAM system. And for our aerosol model, we use what's called a bin bulk aerosol scheme. So we treat all our different aerosol species as being totally independent. We don't think of a small particle, as being a mix of different aerosol species. Instead, they're just treated as entirely independent species and sometimes of different sizes. So we have different sizes for sea salt, desert dust, and nitrate. And then we have hydrophilic and hydrophobic particles for black carbon and organic matter. And then we also have independent traces for sulfate, ammonium, and different sources of secondary organic aerosols. So in total, we have 16 different traces that we use in our system. And each of those different traces has their own bespoke processes that model how the aerosol behaves in the model, but also the sort of transport, the emission and deposition. And you can see some examples at the bottom of the screen here. This is the aerosol optical depth for desert dust, sea salt, biomass burning, and sulfate. These are all valid at the same time on the Tuesday. And you can really see again that storm coming off the Sahara, the dust storm, and how different you can get different quantities coming from. So sea salt, that there's obviously some wildfires burning up in Canada and Alaska. So you can see how we can separate out these different species. And there's also this coupling to our chemical model. So the real question is, with these observations and with this model, how well are we able to capture these dust storms? So again, this is a Saharan dust storm coming off the coast, the west coast of Africa, and going across the Atlantic to the Caribbean. This is one that took place in May of this year. And what you're seeing here is the sequence of the analyses, so the best guess of what the actual aerosol is in the system or in the atmosphere throughout May. And you can really see that storm crossing across the Atlantic there and hitting the Caribbean. In the top left, I show the Sentinel-3 visible imagery and the Sentinel-5P aerosol index of this storm, just to show that we really do know that this is a desert dust storm that's coming off this coast of Africa, and you can really see it in the satellite imagery. And then the individual plots are our comparison to the AeroNet observations. So these are independent ground-based stations. And you can see I have one here in the west coast of Africa, one in the Cape Verde Islands, and one in the Caribbean. The blue dots are the observations of AOD coming from the AeroNet station. The green line is our CAMS model, taking into account all the satellite observations. And then the red line is the CAMS model, but without that satellite observational information. And what I wanted to show first of all is that in general, we're doing quite a good job of matching the highs and the lows coming from these independent AeroNet observations. There's obviously one notable exception to that, and that's off the west coast of Africa, where there was the high values of AOD from this dust storm. I suspect, I haven't been able to verify it, I suspect that is purely because the observations were so much higher than the model that the system considered them to be erroneous, so didn't really take them into account. And I believe that because if you look at the red and the green line, they're very similar, which says that the model with observations and without observations are doing pretty much the same thing over this station. But in other situations, you can really see where the impact has been had of using these satellite observations. So the green line is providing a much better match to the AeroNet observations than the red line. And that just shows the benefit of using these satellite observations within the system. They really enable the system and the model to encapsulate what's going on in reality, even as far away as the Caribbean from the source of the dust storm. And you can see that then at the end of May, beginning of June, where this station in the Caribbean is getting these high AeroNet values of AOD that the model is capturing when it uses the satellite observations. But we don't just verify with aerosol optical depth. We also look at other values, including PM10. So this is all particulate matter smaller than 10 microns. And when there's a dust storm, it can be largely dominated by dust particles. And this is a very important quantity for CAMS to get correct, because it goes into a lot of, well, certainly the European Union air quality legislation mandates that PM10 values should be below a certain amount. And I think other countries have the same sort of legislation in place as well. And this means that when you have a natural source of PM10, such as dust, it's important for countries to understand that this is something that they can't control within themselves. And it also shows the benefit of having a global model like CAMS that's able to track and monitor this dust from the Sahara across these boundaries, country boundaries, to somewhere like the Caribbean, and able to help organizations and countries really understand when it's something they can control and when it's something like desert dust that they can't control. And again, here you can see that the model is doing an okay job. I think in general terms, in background terms, we're perhaps slightly too low with our PM10 values from these AirNow stations in the Caribbean and in Florida. But why I show these plots is just to show that when this desert dust storm hit Florida in June, you can really see that the CAMS model is able to match these elevated levels of PM10. And again, you can see the impact of using the satellite observations in that the green line is doing a better job of capturing those high values of AeroNet and from the AirNow stations than the red line that's just the model by itself. So I've showed some really good results of how the CAMS system is able to forecast and match these aerosol values. But it's also important to look at the individual species. CAMS is one of the suppliers of a dust optical depth forecast to the SDS-WAS regional node, the NAMI node. And what we've supplied them is dust optical depth. It's not aerosol optical depth. It's not PM10. And so it's really useful and interesting to look in more detail at the dust-specific forecast that we produce. And I show here an example from this storm that took place in 2023. And in this case, the desert dust from the Sahara was advected up and across Europe and across the UK. And you can see in the centre there, I have one of the observations taken on the 15th of February. And you can really see very clearly this plume that's coming up from the Sahara and going across a bit of Spain, Portugal, and across the Atlantic, across the UK. And if you look at our total aerosol optical depth, you can see we do a very good job of capturing that plume. We very much match the observation you can see. But if we look in more detail at the speciated optical depths, you can see that although we do see it in the dust AOD, we're also getting some hint of it in our sulfate AOD. And this is a consequence of the fact that we use total aerosol optical depth observations within our system. And the only way we can divide that back and take that information and put it into our 16 different aerosol species is by using model information. And so if the model thinks that what is there is dust, then great, it will update the dust with the observation. But if the model thinks actually there's more sulfate in the atmosphere at the point of the observation, then what it will update is the sulfate, because it assumes the model's correct, that that's the right species to be there. And so it updates it and increases it to make sure it matches the observation that we have. So within CAMS, we've been looking at using the IASI retrievals to try and improve our dust forecasts. And these have already been nicely described and explained by Sophie, but these are different to what we currently use. And again, I use the same example as Sophie of this Godzilla event from this DOMOS project these plots come from now. And it shows this large incursion of Saharan dust across the Atlantic. And you can see from this same snapshot how different the AOD and the IASI observations can be. And this is partly because we're looking at different wavelengths at this point. Also because the IASI observations only pick up these coarse, these large dust particles. But it does give us dust-specific observations. So we can use these just to constrain our dust forecasts without having to kind of understand what all aerosols are doing at this point. They don't have this restriction of only being in the daytime. So we're getting really these 2 snapshots per day globally of what is going on with the dust aerosol. So they have the potential to bring a real advantage to our system in terms of our dust forecasts. And so I show here some plots looking at what the impact is of using these observations within the CAMS system. And I'm now looking at, again, AeroNet comparisons, but looking at speciated AeroNets observations. So what you're seeing here is that you have the red line is the total AOD coming from the CAMS model, the brown line is the dust, and the orange line is the sulfate. And these are from 3 different model runs. So at the bottom left is our operational system. This is what happens if we only use AOD 550 observations within our system. And this is looking at one station in Madrid. And we know that this peak of AOD that comes across is from desert dust, from this storm that we were tracking in February. And you can see that if we're looking at the speciated AOD, although our total AOD increases, it's largely coming from a sulfate increase. Whereas if you look at the top right, and we're now just using IASI observations, you can see that now it's correctly attributed to the dust. And if we use them both together, then you can see that although there's still a slight issue with the sulfate at the start, we're now able to use these IASI observations to really kind of increase the dust as we go through the month of February and capture more of that dust. So this is still work in progress. We're still looking at the ways to best use these IASI observations, but you can see the advantage they bring in terms of being able to produce even better dust forecasts. So I just wanted to summarize what I've spoken about so far by starting with a quote that just highlights how important dust is and understanding and forecasting dust is to people and to European and wider citizens. Sand and dust storms affect livestock, agriculture, air quality, and human health. Intense storms can also force the closing of roads and airports due to poor visibility, deteriorate infrastructure, and strongly affect commercial energy production. So that's a quote that comes directly from WMO SDS was. And it's really one of the reasons that the CAMS system does what it does and why aerosols and dust are such an important part of the CAMS system, is really to try and help mitigate and help improve the situation for people that struggle with these sand and dust storms. And we do that in various ways. I've shown the forecast that we produce, but it's not just forecasts. We actually have an aerosol alert system that people can sign up to and tailor to their specific requirements. And we have policy tools that can help people understand when a PM event might be occurring and what the constituent parts of that PM event are. We also do this routine monitoring and evaluation against the independent observations to really track and look at how well the CAMS system performs. And all of these different tools and this monitoring and also our observational monitoring is all available on our website, which I show at the bottom left there. We also have sort of news items and lots of information on that website that you can use to look and see and understand what's going on in terms of dust from a CAMS perspective and from a worldwide perspective as part of the CAMS system. And also, as part of CAMS, we're always interested in new observations that have the potential to improve the CAMS forecasts, and these are continuously being assessed, and the IASI is a really nice example of that. So thank you very much.
Thanks a lot, Mel. We don't have time for questions because, yeah, I can see one hand raised, but please type your question in the QAI section. If you cannot see the QAI, go to the three dots where it is more, and you will find there the QAI bottom, if you cannot see, in the bottom of your screen, in the menu on the bottom. Sorry, Mel, because we are running a little bit late, and we will come back to this question at the end of the talks. And now it's my pleasure to introduce our next speaker, who is Emanuele Emili. He's based at the Barcelona Supercomputing Center and is one of the staff of this WMO Barcelona DAS Regional Center. He started his career in Italy, then moved to Switzerland for a PhD doctorate studies, and then also France, and finally now is based in Spain, here in Barcelona. And he is the person that is leading the data simulation, atmospheric composition, forecasting activities, more operational activities at BSc, and also is taking part of the developments connected with the operational system that the Barcelona DAS Regional Center is keeping every day. And you can see in the website. And today he will introduce another study connected with data simulation of satellites to produce better mineral dust predictions. And in this case, it is another sensor, is the NOAA VIIRS. And with that, Emanuele, the floor is yours.
Thank you very much, Sarah, for your introduction. So I'm happy to present you some recent results here at the Barcelona Supercomputing Center about using satellites to improve dust predictions. And this is a collaborative work of many people within our groups. I can go briefly through the motivation. We asked the node of SDS was for Northern Africa, Middle East and Europe. And through that, we developed and maintain a reference model covering this area, which is called Monarch. And this model has been used in the past for several research activities and that are using satellites and data assimilation, which has been shown to improve the forecast quite significantly. But since then, it's not been put into operations. So I'm happy to say that we've been working on this in the last few years, and now there is a new operational e-suite that assimilates NOAA-20 since October last year. I would like to take the occasion of this talk to revisit some of the kind of questions that arise when setting up such a system and show some preliminary results. So the challenge are, as we already seen in Sophie's and Melanie's talk, concerning several aspects of the both satellite and model. So first, defining what is the model uncertainty. I will spend a few minutes on that. Then the fact that the dust optical depth is never measured directly by current satellites, so we need to make assumptions on that. And also, I mean, it's very important. We've seen surface concentration are of great concern for several things like quality, visibility. But using a satellite to constrain the total column does not provide a direct constraint on the concentrations, because of the optical properties, as distribution and vertical distribution unknowns. This has to be quantified in a kind of more systematic way. And finally, we initialize our forecast with a satellite, but of course, after some time, the initialization is lost, and the impact of initialization is lost, and we need to assess how long this impact lasts in time. To do this, I'll go through 4 points using our in-house system, which is based on Monarch, which is an online model, meteorological and chemistry model, which is coupled with an ensemble-based data assimilation system. So you have some more detailed information about the setup. This is the setup for the Barcelona dust node, about 10-kilometer resolution covering the whole domain. Perturbations, how to deal with the uncertainties in the model. Depending on the data assimilation scheme, this can differ. In our case, we use an ensemble-based scheme, which is gives a pretty straightforward way to assess uncertainties. It means that you can put random perturbation within the model itself. And those are different ways to do that, from more simple, for example, perturbing typically the dust calibration factor, which is a constant value across the domain, towards more sophisticated perturbation that change as a function of the aerosol size, and through spatial corrections, or not correct, sorry, perturbation that change the dust emission as a function of the location where the emission are done. Those are the first 3 here that have been retained for our first operational setup. We can go further by including perturbation into the dust emission scheme, which is this so-called SGH step, and also in the meteorological fields. What happens when you do all that? Here on the right, you have the histograms of the dust optical depth spread across the ensemble members with all this perturbation. It's important to remember that assimilation schemes like to have Gaussian distributions. So you can see that the simplest approach would perturb the dust factor. Emission factor is not providing a very smooth distribution for the data assimilation. And you see the smoothest one we can get is with this map approach. but also by introducing on the right meteorological perturbation, which has an effect of also skewing the histogram of the perturbation. So this was a preliminary study done in the past to kind of tune the system beforehand. Now we decided to use only 12 members with these highlighted perturbations. Now the observations. When you simulate optical depth, as has been said now before quite some times, you don't observe only dust. So you have the choice to either assimilate the full optical depth, which is here on the top from VIIRS. Just to remember, VIIRS is the kind of spiritual successor of MODIS. So measuring in the visible and providing quantitative, pretty good quantitative retrievals of aerosol optical depth. We decided to go to a kind of a bit different approach, and which considers only the retrievals flagged as dust. You can see this in the bottom plots on the left. So you see that the kind of dust signal is much increased at the cost of having much less observations available. But this is a trade-off that in data assimilation systems can be done, because the observations are assimilated when they are available. Now, what's the impact of doing that? We have here on the first column the operational forecast running today, the dust optical depth averaged for 3 months in the last period, showing the kind of variability that we have across seasons. And on the middle, the forecast initialized with a satellite assimilation. So you can see by looking at the difference on the right that we address one of the kind of biases, systematic biases that we used to have in our system. So it's a bit too much dust on the in the Western Africa. But this correction very much dependent on the season and the month, and indeed shows the complexity of correcting the system, and which only data assimilation can achieve through kind of continuous correction of the dust optical column. Now, if we take this system and we compare it to other systems running daily in the Barcelona Dust Regional Centers, we have here a list of prediction system that use satellite in near real time. We validate those against AeroNet observations that are shown here for some selection of regions in the domain. And in the middle, you have the key information is a bit small, but I will go through a bit through this. The color, focus on the color, it represents the model. You have the correlation on the first column and the mean fractional error on the right column. And there are two kind of typical indicators of the quality of the forecast. And to do that, we only use AeroNet observation being filtered for presence of dust through the low angstrom exponents. You can see that the 3 bars of the same color are the statistical skills for different day of forecast, day 1 to day 3. And I put here some horizontal lines to indicate some kind of reasonable level of accuracy in terms of correlation is 0.6. And mean fractional error is a bit high, but depends indeed on the region, and it's set to 80%. So first result, you can see that the forecasts are greatly improved by data assimilation in our system, because we can compare the colored bars here, the second set with the first. You can also see that the impact of the DA is quite good until the 3rd day. So most of the time, the 3rd day has still better skills than the first day of the forecast without any data assimilation. And third, that with data assimilation, the skills of the system are somehow comparable. So most of the time above 0.6 in correlation for all the system that employs some kind of data assimilation. Nevertheless, there is quite some variability across systems, and since the methodology is not the same, the satellites being used are not the same. it would be interesting to try to investigate a bit more those differences to try to understand the kind of added value of different satellites and different type of observations. It's very important since 1 minute, it's my last slide, I think. Oh, not really. To look also at the ground concentration, and here are some preliminary results showing that with the data assimilation of satellites, even though we do not assimilate surface concentration, there is a significant positive impact, at least in correlation. So when we compare our forecast with set of stations that are exposed to dust outflows. Even though it's preliminary and some more additional time series have to be evaluated. I wanted to finish with an important point. There are always some systematic biases in the forecast, and it's a bit a pity to use satellites in a kind of near real-time fashion without addressing those first. And there is a kind of ongoing study by our colleagues here where they use the same satellite, VIIRS this time on another, sorry, the same sensor, but on board another satellite, but very similar product, to correct the emissions in the past. So looking at like 5 years time series, and here you have an example with emission correction factors that can be derived by this methodology. For example, if you focus on the Baudelaire regions, you can see emissions that have been corrected by a factor of 0.4 to a factor of 0.8, so generally decreased, and with a very distinct seasonal behavior. So what happens if we try to use this information, even though it's not very up to date, into our regional prediction system? Maybe I just will focus on the main outcome, is that of course, you cannot achieve the kind of as good correlation as a full near real-time data assimilation system. This is the one here in the middle. But still, the biases can be improved most of the time. And so I would like to, the biases are here in the middle plot. I would like to conclude by saying that, yeah, there is a good, very good impact of VIIRS. We are going to release this project on the website next week, so it will replace the current forecast system. And I think also that synergy is possible between emission correction and near real-time data assimilation, because they address a bit different errors in the models. What's next? New type of instruments. Some very nice work has already been done using IASI. There are other satellites, for example, addressing size distribution of aerosol particles, but also improved data assimilation through new techniques. I think I will finish here and be happy to take questions later.
Yeah, we will take all your questions at the end of the webinar. Thanks a lot, Emanuele. Remember, you can write in the chat, but it's better to put it in the Q&A section. If you don't have this button, look for the 3 dots plus more, and you can text them there, all your concerns, questions, comments. And if it's possible, we will take care during the talk. And because the lack of time, I would like to invite our next speaker to open the camera. She's Trish Nowak from the Exeter University. She's PhD candidate in this university, and in fact, tomorrow she will defend her thesis. Good luck in your challenge tomorrow. And thanks a lot, even double thanks to be here today, because I can imagine that you are very stressed today. And she will introduce her research, the research that is in her thesis document, that is connected with how we can use satellite data and also information about the processes connected with the sun and the storms to create an artificial intelligence forecast of dust. This is part of the DustNet network that Franco Marenco, if you want, at the end of the talk, you can introduce a little bit more. And today she will introduce the results of her research, and hopefully also the well-deserved for gathering this PhD title in your name in future. And with that, just try to show your screen.
Yeah.
Yeah, also we can hear you very well. The mic is working.
That's easy.
And of course, all this research that also Melanie, Emanuele, and now Trish will introduce is oriented to the provision of tools for creating better early warning systems that can help us to mitigate the negative effects that sun and desert storms pose in our life. Mel introduced that in her final slide is because of the impacts of sun and desert storms in health and economies that is getting more and more important to improve our tools for forecast sun and desert storms, to predict these sun and desert storms, to support those countries that are more affected. But also it's because, yeah, here you are, the screen. And I think that in your introduction, you will stress these points, then I don't want to repeat myself about things that you will present now. And my pleasure to give you the floor and to introduce the satellite-based neural network predictions of Saharan dust.
Hi, everyone, and thank you so much for having me. Sorry for this short delay. Today, I'll introduce you to a method for producing skillful satellite neural net predictions of Saharan dust. I will start this presentation by quickly outlining the scientific problem, and then I'll introduce the data and the dustnet model, and finish by highlighting the key findings. So let's get started. There is 26 million tons of mineral dust suspended in the atmosphere at any given time. Each year, global deserts emit additional 5,000 million tons. About 55% of atmospheric dust originates from Sahara Desert, and nearly half of that comes from a single hotspot, the Bordela Depression. Once in the atmosphere, Sahara Desert interacts with Earth systems in complex and far-reaching ways. It affects human health and infrastructure, alters the Earth's albedo by changing the colors of underlying surfaces. It also plays a key role in biogeochemical cycles, delivering essential nutrients like phosphorus and iron to rainforests and oceans. Dust can even suppress hurricane formation and also helping to replenish the sandy beaches of the Caribbean islands. Those diverse effects highlight why accurate forecasting of dust emissions in transport is so important. Yet, despite the complexity, physics-based models often struggle to produce meaningful 24-hour forecasts, especially when evaluated against satellite observations, like above here, where CAM's model is compared against MODIS data. So the aim of my research was to predict atmospheric dust levels 24 hours ahead, focusing on Sahara Desert, and then I'll finish with a quick look at the global dust belt. So I used aerosol optical depth, or AOD, as a proxy for dust, retrieved from MODIS instrument of both Aqua and Terra satellites. I took the mean between two of those to help me to minimize the missing data, and imputed the rest of them with lattice breaking. The meteorological data came from ERA5 reanalysis across 5 pressure levels, from surface level up to 5 kilometers in altitude. After combining AOD and meteorological data, the inputs consisted of over 7,000 daily records with a spatial resolution of 31 by 51 grid points and 43 features, which consisted of past 1 day of meteorology and past 5 days of AOD. So at any given time step, my model had access to AOD conditions over the past 5 days. To predict AOD 24 hours ahead, I developed a deep neural network model, which we called dustnet. So DASNet is a convolutional neural network that trains in under 8 minutes on a standard desktop computer without any GPUs needed. Once trained, it generates predictions in just over 2 seconds, making it orders of magnitude faster than any physics model. And importantly, it creates realistic-looking results. Here are the predictions created for February 2020 during a large dust storm. So on the left are the models observations, and on the right are the corresponding DASNet predictions. And we can see that those outputs successfully capture key dust dynamics, including emission from the Bodella Depression and the southwestward transport, closely matching what we see in modest satellite observations. Compared to a standard 2-dimensional convolutions or unit architectures, DASNet trains nearly 7 times faster, predicts faster, and achieves lower mean squared error. The best results are shown here in dark teal. The annotated source code for anyone who would like to try it out. The model is freely available and you can download it from the Zenoda repository. Let's look at the results then, which compared the DASNet performance with that of physics-based CAMS model. So statistical evaluations against satellite observations reveal that DASNet predictions align well with modest data, as seen here on the left, where all of the white to blue shades indicate higher R-square values. The widespread blue areas and the higher mean Pearson's R-square demonstrate that DASNet outperforms CAMS overall. But it's also important and most likely interesting to examine precisely where each model performed better. To explore this further, I analyzed the root mean squared errors against modest observations. In the top image, brighter shades indicate better performance for each of the models. The middle panel shows the difference in between those root mean squared errors, where blue areas mark locations where CAMS performed better, while yellow to brown indicates where DASNet had the advantage. And the dominance of those yellow and brown shades shows that DASNet outperformed CAMS on over 95% grid cells. That said, some of the blue areas still remain, but I think we can agree that the advantage is sort of clear here. When we look at regionally averaged AOD, the DASNet achieves a correlation of 0.191 with modest data compared to 0.71 for CAMS. Overall, both of those models do perform well, but DASNet tends to slightly overestimate the higher AOD values. In contrast, CAMS underestimates both the extremes and lower values, while overestimates moderate values a little bit more often. Both results here are, of course, highly significant. So the flexibility of DASNet led me to develop 4 additional models for coarser resolutions, for predicting monthly means, and also for climate applications. And each of those models deployed over Sahara region predicts in less than 2 seconds and significantly improves AOD forecasts over the climatological baseline. And all of those DAS models are, of course, deployable on a standard desktop computer. So I'll finish quickly with a quick look at how the global DAS belt region performed. It's important to mention that the meteorological data included for this model had only inputs on 1,000 hectopascals, which is approximately the ground level, which reduced the number of training features down to 15. So in comparison to the original DASNet model, the expanded model trains a little longer, about 2 hours and 15 minutes, though still on a desktop computer. But despite the reduced feature numbers, the predictions are still swift and are created in less than 30 seconds, yielding improvement of 51% over the climatological baseline. An expanded model also shows strong correlation with the modest data across major deserts and especially the transoceanic dust transport routes. While the performance decreases over the Pacific, which of course highlights areas for future improvement, does not still increase the Pearson's R-square values across more than 98% of the grid cells. Taking all those together, those results demonstrate that satellite-based neural network predictions can deliver valuable 24-hour ahead AOD forecast. Thanks to this fast training and prediction times, DASNet can run on a standard desktop, making it a practical tool for both research purposes and for early warning systems, especially in regions affected by severe sand and dust storms. So that's it from me. Thank you very much, and I do welcome any questions.
Thanks a lot, Trish, for keeping on time the talk. And maybe Mel wants to check with you some results, because Copernicus results, the performance of the two systems, but we will keep it for the end of the webinar, because I still have one speaker or more. Is a forecaster, and is the example on the use of all this work that you are developing in research, moving to operations, and is how we can use air quality forecasting, in that case, sun and dust storm forecast systems, in our daily life. And is Amadou Diakite, who is head of the Weather Observation and Forecasting Service at Meteo Mali Meteo. He will talk about the sun and dust storms warnings that currently they are operating and publishing in the website of Mali Meteo. And Amadou will talk in French. Then I think that it's very easy to follow his slides, even if you don't speak French, because he will analyze several cases in which the use of sun and dust storms forecast products can support decision makers, as Amadou, in the decision of create a warning for the population when these sun and dust storms are going to the extreme intensity that can hit economies and different socioeconomic sectors. Also, you can choose the option, remember, to activate the captions. Is in these three dots more at the bottom. And of course, if it's needed, Amadou, we can do translations from French to English, but I think that for the lack of time, let's try to do the talk in French entirely. And if someone needs more details, we can do some translations at the end, okay?
Okay. Merci, Sarah,
Please,
et bonsoir à tous. OK. Et je vais parler en français. Et le cas que je vais montrer, c'est la prévision de la poussière. Et grâce aux produits que nous fournit le centre.
Attends, parce que l'écran, ce n'est pas partagé. Qu'est-ce que tu voulais que nous partagions l'écran?
Oui, vous pouvez partager l'écran. Et
Ok.
vers la fin, on va mettre la vidéo.
Une minute, parce que
You have the presentation, otherwise Ernest has a copy.
non. C'est la
Ok.
présentation ici. Ah, c'est l'Ernest. Merci, Ernest. Très gentil. Allez.
OK. Bonjour à tous. Je m'en vais vous présenter un cas de tempête de poussière qui est intervenu le 30 juin 2025. Et le 30 juin 2025, en principe, c'est la période des saisons des pluies dans la région sahélienne, en Afrique de l'Ouest. Et souvent, il y a des tempêtes de poussière Et grâce à l'appui du Centre régional de prévision des tempêtes de poussière de Barcelone, qui nous donne des produits, nous avons pu anticiper et faire une alerte pour la population et aussi sur la qualité de l'air. Donc, c'est cette situation que je m'en vais vous montrer. C'est la situation du 30. Donc, bien avant la situation du 30, on avait regardé les produits du centre Barcelone, comme vous le voyez dans la présentation. C'est l'image du 29 qui continue jusqu'au 30. Donc, on voit qu'il y a la tempête de poussière qui est prévue dans le nord du pays, précisément dans la région de Tombouctou. Je ne sais pas si vous pouvez avancer, Sarah. L'ima- Si vous pouvez continuer slide, please. OK. Donc, ça, c'est un produit que le Centre régional de Barcelone a créé pour le Mali, le Niger, le Tchad, la Mauritanie et les pays d'Afrique subsaharienne. Donc, sur l'alerte par rapport à la poussière, il était prévu qu'il y aurait une forte tempête de poussière dans la région du Nord. Et quand on analyse les cartes synthétiques, nous voyons qu'il y a un système orageux qui était prévu dans la journée du 30, comme on le verra sur l'image. Slide, please. Je ne sais pas, on peut passer à la prochaine image. Please, Sarah, could you go to the next slide, please? Yes.
Ce n'est pas moi, c'est l'Ernest qui
Ok,
a le contrôle de l'écran.
d'accord.
Ernest.
Je ne sais pas si ça fonctionne. Je suis en train de montrer l'image des satellites, c'est ça?
Oui, c'est bien ça. C'est l'image satellite où on voit un système organisé qui est au nord du Mali. Donc, après avoir regardé les cartes de pression, nous voyons qu'il y a un creusement, oui, comme vous le voyez sur l'image. Et on a regardé aussi le canal poussière et pour voir s'il y a déjà de la poussière en suspension dans le nord du pays. Donc, ensuite, nous avons analysé les champs de vent. Vous pouvez avancer, Ernest. Oui, si vous pouvez avancer le prochain slide.
Je l'ai fait déjà. C'est le vent que vous
Oui,
voulez? OK.
non, c'est bon, c'est bon. Et sur les champs de pression, ça, c'est le modèle GFS qu'on a utilisé. Et nous remarquons il y a un creusement de la dépression saharienne au cours de la journée. Donc, entre 6 heures et minuit, et il y a une diminution de la pression de 3 hectopascales. Donc, ça, c'était il y a il y a une diminution de la pression. Et aussi, nous avons ensuite analysé les autres paramètres, comme le vent. Vous pouvez, oui. Donc, en analysant les champs de vent au sol, nous avons remarqué entre midi et 18 heures qu'il y a une accélération des vents au sol, surtout dans les régions du nord. Comme vous le voyez, je l'ai encerclé en rouge. Donc, ça, tout ça, et c'est des dépressions qui sont sèches. Donc, sur la base de ces informations, nous avons commencé à imaginer que c'est une zone qui est orographique et plus la baisse de pression. Donc, ces paramètres pourront nous permettre de savoir s'il allait avoir des tempêtes de poussière ou pas. Donc, vous pouvez passer au slide suivant. Oui, suivant.
D'accord.
Le slide suivant, ça concernait les lignes de flux. Oui, ça c'est l'humidité au sol. Une analyse de l'humidité au sol nous permettait de connaître les masses d'air en présence, si c'était le vent de mousson ou le vent d'harmattan. Donc, comme vous le voyez et dans la partie nord, l'extrême nord, la température du point de rosée était autour de 0,2 degrés. Donc, l'air était très sec et au nord. Maintenant, une partie des régions du nord, la température du point de rosée était entre 16 et 12 degrés au sol. Ça, c'était juste pour avoir une idée de l'air au sol. Si l'air était sec, très sec, ou bien si c'était humide. Donc, vous pouvez continuer. Nous avons également fait une analyse de l'humidité dans les différentes couches de l'atmosphère. C'est ce slide qui suit ça. Nous avons fait l'analyse à 850 hectopascales et 1500 mètres. Ensuite, nous avons fait au cours de la journée, nous avons aussi fait l'analyse de l'humidité à 500 HPA et à 700 HPA. Donc, ça, c'est pour connaître aussi le taux d'humidité en altitude. Donc, pour voir si il y a assez d'humidité en altitude, que ce soit pour la formation des nuages, mais aussi pour voir s'il y a les tempêtes de poussière et qu'est-ce que nous pourrions avoir par la suite. Et nous avons aussi analysé les champs de température. Euh, En cette période, il fait très chaud dans le nord du Mali. Les températures tournent autour de 40 degrés au cours de l'après-midi. Donc, entre 15 heures et 18 heures, quand vous allez voir sur la carte, les températures tournent autour de 42 degrés. Et la tempête de poussière que nous allons voir par la suite a commencé autour de 13 heures, 14 heures. Nous avons également analysé les champs de PW, l'eau précipitable, et de vitesse verticale au cours de la journée. Tout comme nous avons regardé les sorties de modèles du Centre européen ECMWF et UK Met Office et pour voir ce que ces sorties de modèles prévoyaient au cours de la journée. Ça, c'était la PW à 925 et la vitesse verticale au cours de la journée. Donc, après avoir analysé tous ces paramètres météo, nous avons également regardé pour les villes de Gao et Kidal, là où l'imagerie satellitaire montrait le système. Et nous avons regardé la valeur de l'eau précipitable qui était prévue par les modèles. Et nous voyons que la valeur de l'eau précipitable pour le 30 était très bas, ce n'était pas élevé. Donc, la probabilité d'avoir de la pluie dans ces zones était très faible. Donc, à défaut d'avoir de la pluie, si un système orageux passe sur un sol sec, les courants de densité qui accompagnent le système, plus l'orographie qui sont dans la zone, participent à un soulèvement de tempête de poussière parce que le vent sera très fort et le sol est nu, sec et il fait très chaud. Donc, toutes ces conditions réunies font que nous avons la tempête de poussière que vous allez voir sur l'image. Mais grâce aux informations que le centre Barcelona avait données, qui corroborent aussi avec la situation réelle, nous avons fait l'alerte pour informer la population qu'il y a un système convectif qui arrive dans les régions du nord, mais que compte tenu des caractéristiques du sol, ça allait soulever de la poussière. Donc les gens avaient commencé à prendre les dispositions et vous allez voir par la suite la poussière. Je ne sais pas si vous pouvez mettre la vidéo. C'était accompagné d'une vidéo. Donc, voici la situation que le système a amenée. Et il y avait une réduction totale de la visibilité avec la poussière généralisée sur toute la ville de Tombouctou jusqu'en Mauritanie. Donc, les gens sont en train de fuir pour aller s'abriter et fuir la tempête de poussière. C'est cette situation que je voulais présenter et aussi remercier le centre pour l'appui qu'il offre au pays et pour les prévisions des tempêtes de poussière. Je vous remercie. Et je m'excuse de la qualité de l'image.
La qualité, oups, la qualité, c'est très, très bon. It's amazing. I mean, this is the kind of severe extreme weather that you are experiencing time to time in Africa, but not just in Africa, unfortunately. It's beyond Africa, and all your experience as local forecasters, it's really welcome. And I would say that we have to congratulate the two representatives of the regional center here, Emanuele and Ernest, for all the support that is given to the region. And please, if you have questions for Amadou, text in the Q&A. I can see some messages and some questions that are being addressed by the speakers. Prish and all the rest of the panel, please, if you can open your cameras for the closing of this part of the invited talks that we have today. It's really my pleasure to listen all of you. Always is my pleasure. And Trish, you have several questions in the Q&A for you. Yeah, just for you. You have a couple of questions. Also, if you are interested to contact Trish, maybe we can share your email, Trish, with the audience, if you don't mind. There are some very specific questions that you can discuss with Ala and Melanie, if you prefer. No, don't be panicking. You can answer them after. No worries. I don't know if there is any burn question from the audience that for Amadou. Also, you can text in the Q&A or in the chat. And I'm very sure that Amadou and the Mel, Trish, Sophie, and Emanuele, or invited speakers, will be happy to answer all your questions. Also, Emanuele is taking care about the high latitude dust. Pavla, no worries. And with that, I want to pass the floor to the last part of today, which is Nichko, Slodovan, and Ernest, who will take now the next part of today's webinar. And thanks a lot for the invitation to be here today. And I hope that next year will be another opportunity to organize this webinar with researchers and forecasters in the region. Remember, 12th July, every year, we are celebrating the International Day to Combat Thunderstorms, and next year, same time, same week of the month of the year, we will be here. And with that, Ernest and Nichko, I will pass you now the floor to you.
Okay, thanks, Sara. In fact, I have a very nice opportunity to announce that this time the winner of the SDS WAS Award for exceptional contributions for SDS WAS project is dedicated to Professor Dr. Emilio Cuevas, Director of the Izania Atmospheric Research Center. So I will just start with reading his short CV, and later I'll say a few personal words to Emilio. Emilio Cuevas Aguillo has the first experience with sand and dust storms and their impacts during his childhood, when he spent some time in Western Sahara, where he lived with his family until he was 13. He graduated in physical sciences, specialty of geophysics, 1985, and physics of the atmosphere, 1986, at the Complutense University of Madrid. He joined the Meteorological National Institute of Spain, IMET, in 1987, and became 2 years later the head of the Izania Atmospheric Research Center. So important point, measurement point, I would say, for our SDS community. So this was, and this is still WMO Go Station for global importance, definitely. He met Professor Dr. Joseph Prospero from University of Miami, the world leader in the study of mineral dust contributions to the atmosphere, and who was implementing the AEROSE project at that time. And Emilio made the first characterization of Saharan dust event over Izania, which constituted a chapter of his doctoral thesis at the University of Madrid 95. In the early 2000s, Dr. Cuevas was invited to Dr. Javier Querol from High Council of Scientific Research in Spain to participate in the development of a methodology for quantification of daily African PM load during the dust outbreaks, which would be incorporated later into the European Air Quality Directive. The Scientific Steering Committee for SDS project held a meeting in November 2006 in Shanghai, China. This was the time when still SDS was kind of idea to be organized. And anyway, Emilio Cuevas, representing Med Service, Spanish Med Service, and was invited and had significant observational capacity on SDS, who presented during the meeting. And so it was kind of decision of that time to combine, to use both operational, observational and modeling research, and to establish the future SDS-WAS system with the first regional center for Europe, Africa, and Northeast, which was specified during this kind of meeting. On April 2026, 2010, the agreement between IMET and the Barcelona Supercomputing Center was signed just to follow up the previous decisions. And under Barcelona Center, who started to host the SDS-WAS for Europe, North Africa, and Middle East, was the important event for our SDS-WAS community. In view of the demand of many national meteorological services and the good results obtained by SDS-WAS, in 2013, the first WMO regional specialized meteorological center with activity specialization on atmospheric sand and dust forecast was created in Barcelona, and the role of Emilio was essential for all these activities. From 2010 until his retirement in August 2023, Emilio worked on behalf of IMET in planning the activities of the operational and research centers hosted by Barcelona Dust Regional Center. So this is Emilio's CV, but I would also like to add few, as I said, personal words. This award is given to Emilio in recognition of his really outstanding contribution for dust storm research. Over decades, he has advanced our understanding of Saharan dust transport, but also reaching and explaining impacts on air quality, climate, and public health related to dust, of course. As a leader of the Izanja Center, he has been instrumental in transforming scientific research into operational forecasting systems and international cooperation. Emilio, being last decades the director of the Izanja Center, largely contributed to studying sand and dust storm process by providing invaluable information of incoming and outgoing dust storms passing over Canaries or his place with measurements, collaborating with Dr. Joy Prospero group and studying so-called Saharan air layer, which impacts our climate, human health, and the environment. So his vision, Emilio's vision, and commitment have strengthened global capacity in SDS early warning. He took active role in supporting SDS WAS regional center, as I already mentioned in his CV. And this center, as a consortium of IMET and Barcelona Supercomputing Center, soon became part of the structure that hosted international and interdisciplinary cooperation between numerous organizations in the region. Furthermore, I'm also happy to say a few personally addressed words to my dear friend and colleague Emilio. During our professional collaboration and establishing SDS WAS, we also at the same time got into nice friendship as well. Emilio, if you are following this speech, I hope that you remember that we met first time in 1993 in Geneva during the WMO GO meeting, and we started to discuss how to design and implement the future WMO SDS WAS. This was very initial discussion between two of us and few other colleagues around. And as a result, later on, it was all the story of establishing formally and institutionally SDS WAS within WMO structure. So during the number of meetings that we had in the meantime, after this important GO meeting in 2003, this was Shanghai meeting, meetings in Athens to implement the plan for the SDS WAS, one of the meetings in Tunis during our activities for the NAMI region, and so on. So this was also one of occasion when I would like to mention that our two families met in Izanja. It was unforgettable time when your Maria and you hosted my Slobodanka and me, when you organized attendance of very nice musical event. So it was the time of establishing really close personal and family connection as well. So at the end, Emilio, I have to say that I'm impressed with your energy to continue your scientific work despite difficulties that you are faced with, and wish you all the best, your Nichko.
I don't know if you can hear, but I want to mention that Nichko was the first award person with this WMO Barcelona DAS Regional Center NICE award. It's always the same sun clock, but hopefully, Emilio, we brought the award to Emilio, as you can see in the pictures. Thanks, Ernest, for that.
Yeah, I see for the first time, by the way. That's really nice.
It is being delivered to the award that Emilio for his large contribution to the success of the SDS WAS together with Nichko. You were the two persons together with José María Baldassano, Xavier Carol, Carlos Perez, the
Yes,
colleagues that were pushing these first initial stages of WMO SDS was. And with that, in fact, I am in this picture, Nick, so it was my first meeting.
Yeah, you found yourself, I guess.
Yeah, I found myself. And just I want to join to your speech to thanks, Emilio, for all the large contribution on this San Andreas Storm initiative that is going beyond Canary Islands and Spain. And he created, together with all of you, we are creating this community of researchers, forecasters, that we want to provide better products, better services, better information to the society. And this is all legacy, I hope. And with that, I hope that Emilio will see the recording at some point. But no worries, the award is at home with him, and he was really happy to receive the award from us on behalf of all of you. Hopefully next time you can propose the next person that deserves to be awarded from the Barcelona DAS Regional Center. And with that, Anna, I will pass you the floor to closing the event. Anna Vukovic, the chair of the regional steering group for North Africa, Middle East, and Europe, but also on top of that, co-chair of the global steering committee of the SDS WOS. And she will have the honor to close the event of today. We are a little bit late as usual, but hopefully you are still here. Then Anna, the floor is yours.
Thank you, Sara. Dear colleagues, dear participants, thank you all for your great commitment, not only to today's meeting, but also to the ongoing work of SDS WOS contributing to this work. We have almost 2 decades of contribution of the scientific community to the SDS WOS development. Nowadays, we actually reached even policy and decision makers, which was a long and hard pathway, meaning that our science actually now contributes and having results to shaping some national agendas and economies. So in changing climate, this interdisciplinary collaboration is more urgent than ever, and sand and dust storms are very complex hazards appearing almost everywhere on the world, threatening health, food security, renewable energy, transport safety, and years of open sharing of data and expertise has actually turned SDS WOS into some mighty platform for communication of scientists all over the world. And also it is engaging with other UN agencies and actually accelerating the practical solutions. So we see more and more results in recent years, and the focus of SDS WOS, I wanted to just to add some history, dramatically expanded since the beginnings. At the first, we mainly track with little of knowledge the great plums from Sahara, Gobi Desert. Now this knowledge increased. Afterwards, the spotlight spread to southwestern and western United States events, especially because raising awareness on the impact on traffic safety, a lot of deaths, a lot of damage, and impacts on health. Then to the Eastern Asia. Now we have also a growing high latitude dust community because of the increasing risk of dust storms due to the heat waves, retreating of glaciers. We have newly emerging sources driven by land degradation, conflicts, political instabilities, but also we have some solutions which we witnessed also on yesterday's meeting of the Asia Node. So as climate change and other issues widens those dust corridors, our task actually remains in continuing improving early warning systems, enhancing monitoring networks, of course, and enabling the use of these early warning systems even to those new communities affected by the unexpected local dust storms. And this is all due to the impacts I have already listed. As Sara always wants to highlight, bringing the products closer to users is our main goal. So SDSW's platform and its growing community and interaction with other agencies and also the governments on national level through different engagements and workshops makes all this possible. So I just want to thank you all being part of today's SDSW's celebration, to keep a good work and your enthusiasm in further work. And also, Trish, good luck in your PhD. This is defense, and that's all. May the SDS force be with you tomorrow. Thank you.
Thanks a lot, Anna, for these last words. I think that all of us, we are wishing you the best, Trish, tomorrow. We're here with you. And hopefully next year you can come as a PhD to do this new talk, maybe. Think about it. And with that, it's late. Next time we have to plan it better, the timings, because again, we are running late this year. And just I want to thanks to all of you to stay still now in the webinar. And thanks a lot for all your contributions, are very important, not just in your region, beyond the North Africa, Middle East, and Europe is well known. Your capacity, your enhanced collaboration, your invitation to other regions to be part of this broad community, then just thanks. And you can catch me anytime. I'm your officer in Geneva. Then anything that you need, you can always contact me, and I will be happy to help. And with that, thanks Emili, Emanuele, Ernest, all the people from the Barcelona Regional Center for organizing this webinar, the speakers for the excellent talks, the participants for the excellent questions. And with that, we can close the meeting, and let's see next year the latest. Bye.
Thank you. Bye-bye.
Bye.